Welcome back. Today we're going to talk about the binomial theorem. Now, that sounds like a super technical name, but when we're talking about the binomial theorem, really what we're trying to do is we're trying to find patterns. We're trying to find more efficient ways, and we're trying to link together some of these combinatorics principles that we've talked about when applying them to algebraic expressions. What I've given you here to start with is a small exercise to kind of help you get into the mode of doing some math, but also to help us have a jumping off point when we start to talk about these patterns. I know down a little ways you've got the answers to these problems, but I want you to think through this for a second as you start to expand these. When we have anything to the 0 power, it's equal to 1, right? And so the point of this, I want you to try to work through and expand these, and maybe you remember some of these patterns. Anything to the first power is itself, and I'm actually going to add in my coefficients even when they're 1, because you're going to see a pattern develop here. When I have a plus b squared, it's 1a squared plus 2ab plus 1b squared. When I've got a plus b to the third, it's 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. How am I doing this so fast? Okay, well, I want you to take a look here for a second. That's a repeat. I want you to take a look here for a second. I think probably up to this point here where we had the squared, you could say, oh, it's this, 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 or this, or this. When you get down into the cubed and the fourths and the fifths and the sixths going up to like the 15th, it starts to get a little bit tricky. And so what I've given you here is a chart that's going to help us outline this, and I want you to notice a couple of things. What do you notice right off the bat? Okay, and so obviously this is a video, so the interaction here is going to be limited, but just take a look at the coefficients, take a look at the exponents, and see what's going on here. The first thing you should probably notice is check out this side. These are all 1s, coefficients. And this side are also 1s. So on the end of any given expression, I have 1s, right? Not a coincidence. Not a coincidence. And as I go down the line, notice what happens here. I've got a 2 on my squared, and then I have a 3 and a 4 and a 5. And I've got a 2, a 3, a 4, and a 5. This is not a coincidence. This is a pattern. And we're going to talk about that pattern in just a second. Let's just keep noticing some things here as we go down this triangle. And so as we look down here, I want you to notice a couple things. In the middle of my 3's here, my cubed line, right? So this would essentially be AB cubed. I've got 2 3's. Is that a coincidence? Well, let's look it down. In the 4th line, I've got 2 4's, but in the middle is a 6. In my 5 line, I've got 2 5's. In the middle, I've got a 10 and a 10. How do these things all play together? There's a triangle, and it looks like this. It's called Pascal's triangle. And Pascal's triangle is built upon several patterns. But as we look at Pascal's triangle, we're going to notice some things, and it's actually going to help us with this problem, with problems like this, pretty effectively. Notice on the sides here are 1s. Well, as I go through my connections here, every diagonal is going to give me an addition problem. Okay, so check this out. I've got 1 plus 1, so together those make 2. 1 and 2 make 3. 1 and 2 make 3. 1 and 3 make 4. 3 and 3 make 6. 3 and 1 make 4. So these sums, as I go down, make the next line. Everything is interrelated like that. How does it start? Well, it starts with a 1, and then a 1 and a 1, and then a 1, 2 and a 1, and then a 1, 3, 3, 1, 1, 4, 6, 4, 1. And so every line builds upon itself. Where do these come from? Well, they actually come from combinatorics. And what we're going to talk about here in just a second is how do all these things go together? So the binomial coefficient. When we look at the binomial coefficient, we've got a binomial, a plus b, which is what we're dealing with up there, to some power. And the binomial coefficient, the cool part about this is The coefficients are defined by n combined r at a time for r equals, and then that's 0, 1, 2, etc. Well, what does that mean? That's it. This is an explanation of that. By NCR, here's what I'm talking about, because you're probably like, I have no idea what he's talking about right now. It looks like this. This is another way to notate this. NCR, when we stack n over r, it looks like this, where n is the exponent, and r is the term. Okay, what does this actually mean? Well, just take a look here for a second. The fourth term of a plus b to the sixth looks like this. 6, n is the exponent, 6, and I want the fourth term. And it's going to be a cubed b cubed. Well, how do I know that? Well, take a look up here for a second. Let's look at my a plus b squared line here for a second. My first term, my exponent matches, right? So my third line matches. My third exponent, or my fourth line, so my a plus b to the fourth, which is actually the fifth one, but a plus b to the fourth, the first term, the exponent matches. And then on my a's, it's decreasing, 4, 3, 2, 1. At the same time, the exponent on my b is increasing. And so essentially, I could rewrite it like this. A plus b to the fourth is equal to 1a to the fourth. And then as I go down subsequent terms, as I go across subsequent terms, the exponent on a decreases. So plus a cubed plus a squared plus a to the 0. Well, check this out. I don't have to know how to do this algebra to be able to notice this pattern. Now, you do know how to do this algebra, but the pattern is going to help me define how many terms. So check this out. In my a plus b to the fourth term, I've got 1, 2, 3, 4, 5 terms. How do I know? Well, it starts with my exponent matching my original exponent, a to the fourth. Then my a steps down, 3, 2, 1, 0. A to the 0 is 1. And my b exponent steps up. Check this out. In my first one, I've got b to the 0, right? A to the fourth plus b to the 0 is a to the fourth. Well, then my b steps up. My b steps up, b squared, b to the third, b to the fourth. And at the end, check it out, 1b to the fourth, well, 1a to the 0, b to the fourth. What does my coefficient do? My coefficient is defined by this Pascal's triangle. So I go to my line that has my 4 in it, so it's my fifth line, so this is the fifth line, but it's the 4, starts with the 4. And so my coefficients are going to be 1, 4, 6, 4, 1. So I didn't have to do a bunch of algebra. I didn't have to stack a bunch of terms on one another to be able to define this. So under my noticings tab, I'm jumping around a little bit, but exponents on A decrease left to right. Exponents on B increase left to right. And my coefficients defined by Pascal's triangle. And my line of Pascal's triangle is defined by the line -1 would be my exponent. So if my line, my exponent 4 would be the fifth line. Okay, so how would you know? Well, it's the first number, the first non-1 number, right? So a plus b to the fifth. How do I know which line to use? Well, it's the line that has 5 as the second term in it. Okay, so the other way to do this, and this is where Pascal's triangle comes from, is my NCR defines my term and my exponent. So if I want to find the fourth term, right, the fourth term of a plus b to the sixth, I don't have it here, but I could do it. A plus b to the sixth would be fairly easy to define, right? Because let me look at Pascal's triangle. I'd have a 1, 6. This would be 15, right? Because 5 plus 10. 10 plus 10 would be 20. 10 plus 5 would be 15. 5 plus 1 would be 6, and then 1. This is the seventh line of Pascal's triangle, so that my ab to the sixth. So what would my exponents be? Well, I'd have 1a to the sixth plus 6a to the fifth, b to the first. How did I get that? A steps down 1, b steps up 1, plus 15a to the fourth, b squared, plus 20, a to the third, b to the third, plus 15a squared, b to the fourth, plus 6a, b to the fifth, plus 1b to the sixth. You define the coefficients by the line, and then the exponents just step down. A to the sixth, a to the fifth, a to the fourth, a to the third, second, first, 0. And then the b steps up. 1, 2, 3, 4, 5, 6. You could find any of these, guys. You could find any of these. And so my fourth term of a plus b to the sixth should be 6 choose 4. So this is 6c4, a to the third, b to the third. Okay? This one doesn't want me to use Pascal's triangle. It wants me to use a calculator to compute the binomial coefficients. How am I going to do this? Well, on our calculator. What I just told you was you can determine the coefficients by NCR. So the binomial coefficients are defined by NCR. Well, what I can do is I'm going to have 6 coefficients here, right? Because if I have 5, this means 6 coefficients. And the beauty of this is I can check it using Pascal's triangle. I am going to do 5 because this is my exponent, C, and then what I'm going to do is I'm actually going to define a list. So I'm going to do this all at once using my calculator. So instead of doing 5C1, enter, 5C2, enter, 5C3, da 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 da, boo, okay? I'm going to define all of them at once. So I'm going to go 0, 1, 2, 3, 4, and 5. Why did I start with 0? Well, I've got to start with 0 because that's my 0 term. My first term is defined by that 0. And so when I put this into my calculator, I'm going to hit my math button. I'm going to go over to probability, and I'm going to put in NCR. So show something that looks like this, right? 5 NCR. And then my little braces are going to be on my second parentheses button, and I'm going to put 0, comma 1, comma 2, comma 3, comma 4, comma 5, and close my braces, and check out what it gives me. Spits out that line of Pascal's triangle. So literally, when I put this in my calculator, it spits out this: 1, 5, 10, 10, 5, 1. Well, check it out. Go up to the fifth row of Pascal's triangle. Boom, right there. 1, 5, 10, 10, 5, 1. That's another way to do it. Okay? So Pascal's triangle is defined by this NCR. Well, if we were going to draw one out, I'd go 1 and then 1, 1. Well, then how do I define my next ones? Ones always go down the sides. In the middle, come together these terms. 2. Ones go on the outside. Together come these terms. 3, 3. Ones go on the outside. Together come these terms. 4, 6, 4. Notice, My lines, this is my 0 line, my 1 line, 2, 3, 4. There's always one more coefficient than line number, and I define every single one of them by the line before. Okay? So, find the coefficients of this expression a plus b to the 6 using Pascal's triangle. We kind of already did this, but let's look at the 6th line here. How do I know it's the 6th line? Well, it's got a 6 right here as my second term. So 1, 6, 15, 20, 15, 6, 1. So 1, 6, 15, 20, 15, 6, 1. They go like this. A to the 6th, B to the 0. 6, A to the 5th, B to the 1st. A to the 4th, B to the 2nd. A to the 3rd, B to the 3rd. A squared, B to the 4th. A, B to the 5th, B to the 6th. Plus, 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 plus. That's exactly how it goes, guys. You define the coefficient by the row of Pascal's triangle, or you could do, this would be 6, define your number here, 6C0. That's it, guys. That's all there is to it. Binomial theorem helps me define this. Binomial theorem just says that if I have an expression a plus b to the nth power, it's equal to nc0, so whatever my exponent is, c0, a to the n, b to the 0, plus n c1, a to the n minus 1, b to the 1st, plus dot, dot, dot. N choose r, and then I'm going a to the n minus r, b to the r, plus ncn, b to the n. Well, how does this work? Well, basically what it's saying is, look at my coefficients. I start out with a to my nth power. Then I step it down 1, step it down 2, dot, 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 all the way down. B starts out at 0, steps up 1, all the way down until you step it up to it meets that exponent there. So, find the coefficient of x to the 10th. Oh, the other thing is this. My two coefficients, check it out. 6 and 0 add up to 6. 5 and 1 add up to 6. 4 and 2 add up to 6. 3 and 3 add up to 6. Exponents add to n, nth power. Okay, so if it's the third power, then the exponent's always going to add up to 3. Well, if I've got the x to the 10th of x plus 2, I know it's going to be x to the 10th, and my n, so this is n, right? X to the 10th, it's going to be 2 to the 5th, because these two things add up to 15. Okay, they've got to add to 15. So those two things add up to 15. How am I going to find my coefficient? Well, it's my x to the 10th term. So let's take a look here. I could go to my 15th line of my Pascal's triangle here, right? And so this is a to the 10th, no, a to the 15th, 14th, 13th, 12th, 11th, 10th. So this is a to the 10th right here. So I know that this is going to be 3003. But if I want to find the coefficients of x to the 10th power, I know that that's going to be x to the 15, x to the 14, x to the 13, x to the 12, x to the 10, x to the 11th, x to the 10th. 1, 2, 3, 4, 5, 6. Okay? So my exponent is going to look like this. I'm going to have 15, 0 on this one. 15, 0. This is 15, 1. This is 15, 2. This is 15, 3. What am I doing? I'm saying you either look up on Pascal's triangle if you've got a big one, or you use your NCR formula to find that exponent. 15, 4, and then this one would be on the 10th power, would be 15C5. X to the 10th, 2 to the 5th. Okay? So 3003 is 15C5. So let's do one more example here where we're finding the coefficient for a designated term And there's a little wrinkle here because it's a subtraction problem. Anytime you see a subtraction problem in one of these binomial coefficient problems, you really want to rewrite it as an addition problem. So this is really equal to x plus a negative 3 to the 5th power. What that does for us is we can expand this whole thing. So we could say something like this: 5 to the 0 of x to the 5th, and then it's going to be, my b term is now negative 3, so negative 3 to the 0. And if I keep going down, it's going to be plus 5, choose 1, x to the 4th, and then negative 3 to the 1st. Well, you can kind of see where this would go then, right? Because if I'm looking at this negative term here, whenever the power on that negative term is odd, I'm going to have a negative coefficient, right? And so really what happens is, and this would go all the way down. So if I've got, so this would be x to the 5th here, right? Because this would be 1 and this would be 1, so x to the 5th. Plus 5 combination 1 would be 5 times x to the 4th, and then times negative 3 to the 1st. Well, now my coefficient isn't 5, right? My coefficient is actually made up of 2 parts. It's 5 times a negative 3. And so when they're asking me for this coefficient, it's not just Pascal's triangle. It's a combination of Pascal's triangle and that b term. So it's going to work the same way if I have, like a 2x minus 5. Well, then this like 2x to the 3rd power would actually be equal to 8x to the 3rd. Okay, so anytime those terms inside change, and I have a negative or I have 2x in front, those are going to make my coefficient change and take into account Pascal's triangle and whatever it is. Anyway, so how do I find my x to the 4th term? Well, what I'm going to do is I am going to say, so to finish this thought, this would be negative 15x to the 4th. Well, if I'm going to actually do this problem here, segment it off, my x to the 4th term is going to have a negative 3 term that's to the 1st power. And obviously I just did this, but this is how you would write it all out. Because these two things add up to 5, so 4 and 1 are 5, and then my coefficient from Pascal's triangle would be 5, and then what would match is the 1, and so it's 5, 1, x to the 4th, negative 3 to the 1st power. You could do this for any power, and sometimes they're going to give you an x to the 20th term or something huge to try to confuse you, but that's how you're going to pull out what you need to have information-wise, negative or positive, and coefficients-wise to determine the overall coefficient. So the answer for this one would be that negative 15 number. Thanks for watching, guys, and we'll see you next time.